Swayam Prabha. Digital India. Educated India.
If we are going to store 50 million tons over 30 years, how much can we get from the MOFs, MOF people, right? So we have a supply chain problem. I think that's something that we should all be aware of, that we are designing everything to capacity. We have storage. It's interesting, in the US, when I talk to capture people, they say capture part is easy, we can do that. Storage is hard. You ask me, I say storage is easy, capture is hard. Sometime or the other, we have to get together and define what volumes we're talking about. Something might be easy, doesn't mean we have it at scale. The part which might be doable are simpler technologies of capture, where we are looking at point source capture, very concentrated stream of carbon dioxide, which is easier, and separations might be the easiest way to get to the volumes that we're looking at to store. We don't know. We don't know how far we will get with all of the other capture technologies. That becomes really challenging. For me, it has been very interesting to get a crash course on all the capture technologies that are being thought of, but also looking at the sobering view of saying, how much are we really getting benefit from? In some cases, it also leads to the question, if you look at this one project that we have, the total amount that we have is 40 million to spend over 30 years. Over 3 years. 40 million over 3 years, piece of cake, right? I can do that in 3 days, not a problem. The question is, what are we getting benefit for? Is that money better spent in efficient development? Right? So that's something that we need to ask ourselves, because it's my profession, right? It's nice for me to have this money to drill a well, do all the science, all of that. But if I'm looking at a true advantage to the problem of greenhouse gases, then we need to do a different calculation. Then we need to come in and say, how much of a difference will this one make? If we have a reduction of 50 million tons over 30 years, we will need multiple such projects, not just this one. If we have 10 such projects in US, and we have at least that many projects of large capacity in US, and we have another 10, 15 in Europe, each one of them requiring 1.5 million tons per year, we need to have the capacity to capture that amount of carbon dioxide to feed these projects. The geoscience, the engineering aspects, the part of drilling a well, keeping it open, is not a cheap thing to do. And so every day that you spend on the rig, if you're offshore, is about $1 million a day. If you're onshore, $100,000, $50,000 a day. That money goes very quickly. And so if we have longer wait times, our well falls in, it starts to close. If it starts to close, we need to bring the rig back again at $50,000, $100,000 a day, or $1 million a day if we are offshore, to reopen the well reperforate, reprepare. So there are considerable supply issues that need to be met. There are considerable logistic problems that we have to face. That doesn't mean we don't do it. Again, that means that we have to address those problems and not look at the solution from a very narrow window. It also means that every chemical engineer needs to have a geoscience information. Every geoscientist needs to be partly a chemical engineer to see what the challenges are, what is being faced, and what quality of carbon dioxide can I expect when I plan my project, right? In the case of the part that we are planning, we have, let's see where we are. This is what the area looks like. We have one part, this is one zone. You see the foothills in the background. That's, oh, I was told to use the pen. Okay, so here are the foothills. Oh, come on. So that's the foothills out here. This is the location of our west side well. Out here, some cows, brushland mostly. Nothing is grown here for agriculture. The objectives are to prove up a fairway. We think that the area is much larger. There was a question that was asked, what is the area that you expect? We expect something like on the order of 100 kilometers. North-south, 50 miles. We think that is absolutely doable. The width might be 10 miles, 15 miles, we don't know. That's the part that we are now planning. The second part of that is community engagement, to make sure that we have benefits to the society where we are working in. Climate change, temperature reduction, global warming are fuzzy issues if you are struggling to put food on the table. If you're struggling to put your kids through college. And so people really don't care. Yes, they might be struggling. Yes, they might have very large snowstorms coming through, tornadoes coming through, but those are transient. Children's education is there to stay. Payment for that is there to stay. So all of this is stuff that is being done by people who come from Denver, city folks. This is rural, as you can see, this is rural, right? So that's the second part on defining how do you manage and what does it mean to have social engagement. What is a consent-based siting? Means you site your project, you locate it with the consent of the people that you are placing it with. So in that we have 2 science wells, 3D seismic data. There will be three separate surveys. One is already complete and I'll show you some of those. We will have aeromagnetic survey. That's to locate any metal, and mostly that metal we think will be by way of undocumented wells, coast wells, abandoned wells that have the potential to be leaking into the subsurface, or that might prove to be leaks for when we start to inject. In the US, every injection requires a class 6 well permit. When we talk about supply chain and the rest of the work, I will take you through a class 6 well permit to say these are the types of information that have to be supplied to the environmental agency. The second part is, third major part is why do it there? How do you convince people? What jobs are you creating? What are you doing with inclusion? How many people are going to work on it? What type of people will work on it? And then finally, there is the environmental protection. This looks like nothing is here, but we have a few protected species that need to be taken care of, that we need to say we will be at times when they're not breeding, when they are migrating and they are not in the area. There is in east of Chico Basin, there is a waterway, and so that houses migratory birds. We also have a problem of getting the carbon dioxide to the site. As you can see, there is nothing here. So whatever we put in has to be either trucked in or put in through pipeline, which means this area gets cold. In the winter, it gets very cold. It has very large amounts of snow. So if we are putting carbon dioxide here, we need to make sure that it's still flowing in all types of weather. And then we have agreements that the company is to make to get people to agree to supply their carbon dioxide, because it's a commodity. Now it becomes a commodity. We have designed a site to store. Now we need to have profit sharing with people whose carbon dioxide we will store. This is what the location looks like. We have these squares mark seismic data. We have already collected this square of seismic data, and I'll show you that. This is the east part that we will collect next, and then here is the next patch of seismic data that we will collect. The circles here mark aeromagnetic data. This is data that we will collect on a drone. So we have magnetometers that will be mounted on drones, and we'll have students going out and mapping various paths, flight paths of the drone. We think that the entire area of storage could be like this. We could have some sort of orientation. That's what geology from further north has shown us. This is the general stratigraphy. This is what the rocks are like. We have the drinking water is up to here. That's about 4,000 feet below, about over 1 kilometer of shales, mostly shales, some sandstones, and shales and so on. And then we have a very nice evaporite, this mainly anhydrite, which means it's not reactive, it's very low permeability, it has very high stiffness. This is going to be our shale here. This is the confining zone. Here is our primary target that we think will be about 50 feet. We have another confining zone below, so we know it will not go below that. We have a secondary target out here. These are stacked pays, and these are carbonates. This one is a sandstone. This is quartz, mostly sandstone with some amounts of clay. Out here, if we have to we cannot use this and we have to go deeper, then we are dealing with a carbonate, which makes life a little bit more difficult. There is lower porosity here, lower permeability, but there is a potential for reaction, which is good for fixing carbon dioxide, which is not so good for seismic interpretation, for mapping, because it's too stiff. And so that's what the location looks like. We have one well planned here and another one planned here. We are not so sure whether we want to use this location as well or not. We might, depending on what we find. We still don't know what to find. We have not drilled the first well yet. Here's what the schedule is. We did all of the work up front, gathering every type of information, all the geology information, the supply information, what carbon dioxide suppliers exist in the region, what the geography looks like, what the population is like, where are we going to drill the well, what exists in the area, what might we be potentially damaging. Once we had that location identified, the geology more or less worked out, we put in our proposal, and then we had an award. We had the award last year. I was on sabbatical and I cut short my sabbatical because we got the award and I needed to be back. That was in April of last year. We signed the project 2 months ago. Today is December, 3 months ago. That's when we signed the project. This was a long negotiation because the government wanted us to prove every little point about environmental safety. We did the first seismic. We could not wait for the award to be granted, so we already did one seismic here because we needed to get the strat well identified. Using that seismic, we identify location for the first strat well, that is a stratigraphic well. That means a stratigraphic well means we will drill this well to establish this sequence with all of the properties that are there. In this place, we will take core to get strength, fracture strength, to get storage capacity, all of those assessments. We will have these formations here as well in the lab, looking at the diffusion coefficient through them. What is the seal integrity, storage capacity, seal integrity. If we have very low salinity, in the US, 10,000 parts per million total dissolved salts, below 10,000 parts per million total dissolved salts means it's drinking water. If we have below 10,000 ppm TDS here, then we will have to abandon this one, go lower to the carbonates in the lower section. We think this part might be okay with salinity. That's what geology has shown in the northern region where we do have wells. Okay, so after we drill the well, then we do the first 3D seismic. We need this 3D seismic to have baseline before we start injecting. So this becomes our baseline for after when we start injecting. After the first year, we start the pipeline engineering study. How many pipelines do we need to lay? Where do they need to go? From what point to what point? Who is going to be the supplier? How much can they supply? What should this be designed for? Once we have that completed, we will put in for a Class 6 permit. A Class 6 permit today, if you put in for an EPA Class 6 permit, takes about 1.5 to 2 years to get through. If we put one after year 1, this will be July 2025. The earliest we can think of injecting is July 2027. So it's a long-term project. We are in for the long haul. Once we have this together, then we drill the second well. And we do exactly the same thing for the second well. This is when we've submitted. Now we start in the third year, end of the third year of the project, we start applying for permits to build injection sites. We still don't have the permit to inject yet. In anticipation, because we know that if this is submitted only if we think we can fulfill all the requirements. If we cannot fulfill all the requirements, we do not submit this well, and this becomes a science well. That's what is called a dry well in the oil industry. Then all of our money is on this second well to make this work. Okay? So that's the part which is unclear. We have a very extensive community benefits plan. we have our my co principal investigator, my partner in this. One of them is a social scientist, so she takes the lead to manage all of this part. I will not talk about this because I don't understand much about community benefits. I can speak the language, I don't do the work myself. This is from summer this year. We had the trucks out, the vibes out, the vibrometers. This is the source. So these trucks, if you see over here, they have a platform that they put in the ground. The whole truck lifts up, and now you start vibrating these to put in vibrations inside the earth. The geophones are distributed everywhere. Each one of them has a GPS, so we know exactly where they are, and we get a seismic acquisition of subsurface reflections. Okay? So that part is what is being done now. This is what the seismic looks like. This is the first view on seismic, very fresh. Maybe we got this to show 3 weeks ago. The scale here is on time. I'm not showing you the time scale because these are data that are confidential. Another interesting thing that's happening in the CCS world today is people are buying up land for potential carbon storage locations. And so if we are planning 3 wells in the area, we want to make sure that we have that project tied up, or our commercial partners have the project tied up and the land leased. This is the basement. So what we're looking at is this is lateral and this is depth in time. This is the time it takes for the reflections to come back. Out here, this is a slice that is located in the target formation. This is what the target formation looks like. We have a slight dip, and we think that is enough to be the potential trap because of that dip. That dip should be enough to keep carbon dioxide in place. Sorry? Lines is the formation. So this is the sandstone formation that is our target. It's a name. Mississippian, that's the basement formation name. This is the basement. So usually, and these are all sediments above, this is usually crystalline basement. One thing that gives us a little bit of concern is that, and I'll show it to you in the next, I think it's clearer, there is a small fault in the basement. So we need to know exactly what that fault is, what is the reactivation stress for that fault, so that we do not load up this one too much, reactivate the fault here. But for the most part, this looks very benign. There are some shallow faults, but none of them cross over to where we are. That's another view, and the Lions formation here. This is our target, Lions formation, target here, basement out here. Sorry? The color maps the dip. So you have a dip is sort of, it's not flat. It's not flat like this, but it's dipping this way, right? So that's what that marks. So this is a sort of a incline. Most probably the other arm is somewhere further away, but we are looking at this sort of an incline. So we can say that we would like to inject somewhere here, so that that dip keeps it in place. So right now the target is to drill on that northwest region, northeast region. We take this structure with the dip that we have, plus the lab measurements of porosity permeability, and do the structure maps for reservoir simulation. Yes? It doesn't matter, yeah. So, this has no dip, right? So, the dip is just the degree of tilt, right? So, if there is no color change, there is no tilt. Here we are going from hotter to colder colors, that shows you, and it's a consistent change, that shows you a dip. Here it's going all over, there is no lateral consistent variation. So, if there's a lateral consistent variation, that tells you some sort of a direction is going on. Here all over the place means there is undulations. It's classified by being a very stiff place, a very stiff formation. Mostly it is a crystalline basin. It could be igneous or metamorphic. In our case, this is metamorphic. So, that a concept? No. Igneous is rocks formed with lava. These are old igneous rocks, or it can be all of this sedimentary and the igneous rocks that have changed due to temperature and pressure, and these usually are very, very stiff formations, not very porous. Most of the porosity is gone. So, this is defined usually as basement. Okay. The part which we want to also discuss is storage permanence. What I told you for this formation, this is a saline aquifer. It's a sedimentary rock. It is mostly non-reactive. The material here is sandstone, and sandstone with some amounts of clay. If there are reactions, the clays would react, but that's about it. Nothing else is reacting. If we want to have permanence, then we want to go for reactive formations. So, for example, in this case, we would go to these ones here. These are carbonates. So, we would be targeting these blue carbonate beds. That's one option. Carbonates are not that good because what we are doing is constantly recycling. You have calcium, you precipitate, dissolve calcium, you reprecipitate, you're really not doing much. You're changing the formation, but you are not permanently storing. What we can do is look at other reactive formations. So, we can optimize mineralization in formations like this. This is Deccan basalt, and these are different textures in Deccan basalt. So, there is a very large potential to be storing carbon dioxide in formations like these to have benefit of permanence. What we call permanence means that you put carbon dioxide in place and you come back after 10 years, that carbon dioxide doesn't exist anymore because it has reacted and formed a carbonate rock. Okay. Now, the challenge we have here is mapping how much and where does any residual carbon dioxide stay, or how much have we mineralized, where have we mineralized. We can get alteration, but we need models. We need what are called THMC models. Those are thermo-hydro mechanical chemical models that incorporate all of the properties that are affected either by hydraulic properties, by mechanical properties, by chemical properties, and by temperature changes. We do get a change in mobility. So, that is a flow model that needs to happen where you are modeling reactive flow. And finally, our tools are too coarse at the moment to have a quantitative mapping of what's changing in the subsurface. So what exactly are we looking at? This is work that is being done by Thomas Manika, Ryan Polea, Katerina Prof, and two more colleagues, and they are determining the Manika and Katerina are at Mainz, Ryan is at Virginia Tech. They are looking at mine tailings. So they're taking mine tailings and they're adding carbon dioxide, and the host rocks are mafic and ultramafic. That means mafic rocks are basaltic. Ultramafic are even more have higher contents of magnesium and calcium. Magnesium and calcium are very reactive and they can react with carbon dioxide to form a carbonate. And so what they are investigating is what are the kinetics of alteration, how fast, how much does it alter, in what form does it alter. The benefit of this is because it's mine tailings, it has already been crushed up. So there's a lot of reactive surface that's available. They are geologists, all of them, and they investigate things on a small scale to say how much are things changing, where are they changing. One of the big things for us is to know where the alteration takes place. What is the location for alteration? Okay. This is a typical picture for, this is an acoustic scan, true color in gray shade, and this is a false color image of fusions in cement. So this is the cement host rock. These are fragments of granitic rock. These granitic rock means there's a lot of potassium, sodium and aluminum, not as much magnesium and calcium. And so you see some reactions, some fracturing here. There is a sort of a gel forming out here, but you compare that with a rock that has more calcium and magnesium. Now you see that there is enough of a leaching out of material. This here box represents that area. This is 1000 microns, 100 microns. So there is a lot of reaction that's taking place. If we force it, nature does the work for us. This is a natural rock, a feldspar and a feldspar, and this is the reaction that's forming at the boundary here. You can see out here, you can see over here all these growths happening. This is a natural rock. This happens by itself over millions of years. What we are doing is we are trying to speed it up and have the reactions happen in years, if not weeks or days. So the second thing what happens is we are going into saline aquifers even if nothing is changing. This is a sandstone, this is quartz. Quartz does not react. This is before we inject carbon dioxide. Here's brine in the pores, quartz out here. As we inject carbon dioxide, these are micro CT images, X-ray images. This bar gives you 25 microns. As we inject carbon dioxide, you see precipitation of salt out here. Now for us it's interesting. So there are two things to take away from, as a geophysicist, there are two things. One is that the salt is being precipitated is interesting. For a geophysics perspective, the location of this precipitation matters. If I get precipitation out here in the contact zones, then I stiffen the rock a lot. If I get precipitation out here on the pore boundaries, then it doesn't matter to my seismic waves. So my imaging part my indirect measurement is critically dependent on not that precipitation is taking place, but on the location where precipitation is taking place. And so, and we exploit that because we develop models, we know how to model the saturation here. Any change from that is due to chemical reactions. And so we have, the signal we have is a velocity, sound wave going from this side to that side. That's all we have. We have the time that it takes for a sound wave to go through. Now we have two effects that are changing the signal. First one is, instead of brine here, now we are encountering carbon dioxide on part of the way. The second one is salts that have now strengthened, suddenly a stiff matrix here that speeds up the sound waves. And so we need to separate between the presence of two different types of fluids and the presence of this reactive material. This is work that is done by Duran et al. This is from Ludmila Adams' lab in New Zealand, and they are looking at the change in velocity for different porosity rocks. This is very typical porosity in basalts. Yes? Sorry? In the last slide, yeah. Yes? How much time did it take for salt? This would have been a couple of days, 1 day, 2 days. So this happens fast. And this is sodium chloride, the solution we had. So the question was, how much time did it take to go from here after injection to form the salt crystals? We forced in this case, we forced the issue by having a supersaturated salt with sodium chloride. But after we did this work, I started thinking back to basic chemistry, right? You don't need a supersaturated solution if you mix salts of different solubility. So if I mix sodium or potassium chloride, which is common, with calcium chloride or magnesium chloride, which is also common in formation water, then changing, drying out the brine will come at a cost of precipitation of the low solubility salt, because the high solubility salt wants to expand. So that's the part, and we did the calculations there. We stopped because we said this is really happening and we know it's happening, it's interesting, but not right now for us. But that's something that would be really typical. It does happen within days, it doesn't take very long. And the whole thing is dependent on how much water dissolves in carbon dioxide dissolves in water. So what is the drying out effect? Because you're enriching the remaining brine with salt. So the salinity of your brine is increasing. And that salinity increase comes at a cost of low solubility salts. Yes, so it increases pore pressure. It also, you're right, because you see over here, that's the brine, right? So there are a couple of effects going on. The brine is becoming more saline. If it's becoming more saline, then the viscosity is changing. As the viscosity is changing, the dispersion is changing, the seismic dispersion is changing. So there are, and there's an additional effect. I have carbon dioxide over here. So think of a seismic wave, the sound wave that's going through. If a sound wave is propagating here, then this thing moves like a meniscus. It moves in and out because you're pulsating a sound wave through here. So as the wave moves through, you have a meniscus over here, and that thing goes in and out. Very typical, like a eardrum. If you think of an eardrum, you have you hear the sound because your eardrum is flexing from the partial pressure, from the pressure of the air wave that is that is being deformed. That's exactly what we are sensing here, just on a different frequency, not on a audible frequency, but a much lower frequency. But this effect is exactly the same. Yes. Yes, yes, yeah. So the pore pressure would be increasing because we are injecting carbon dioxide. The brine is not going anywhere, so the whole pressure is increasing. And so that part will change also the seismic waves. So your effective stress is reducing in a way, right? Because your pore pressure, internal pressure is increasing, your overburden is staying the same, which means the stress on the grains is reducing. So when you do that, then your porosity increases a little bit, and that porosity increases what we get as storage capacity. Okay. Good. Okay. And we map that through changes in velocity. So these are compressional shear velocity measurements from various types of rocks, because you can get different changes. What you can also get is a change in pore size distribution. These are NMR data for two sandstones here as a function of pressure. But you can think of these being basalts. You have major pores and then you have smaller pores. What we are interested in is, will all of these pores change, or like over here, only some of the pores change, the large pores stay the same? We don't know. That's the part which we are all trying to address, because we have so little understanding on where the reactions happen. Most of the kinetic studies, the chemistry work has been done on powders, on chemisorption type of work. We do not have anything where you have a change in the access versus reactivity of the surfaces. So you can have very large access of low reaction material and low access to high reaction materials. The competition between access and reactivity is really something that we don't know to date. This is another way of looking at it. These are complex conductivity measurements, and as you increase stress, as your pore size changes, you see a shift in the principal frequency. So the spectra are changing, and as the spectra are changing, we can interpret them as a change in the pore size. Think of these as being pore deposits. If there is pore deposits that are happening, then your pore sizes are changing, and you would go from here, large pore size, to here, small pore sizes. In the case of basalts, I think we looked at this in the first day. Did we look at this picture on the first day? This is a hand specimen of basalt, and it was exposed to DI water with carbon dioxide for 30 days, for a month, at 90 degrees C, 10 MPa, 100 bars. And what you see is a complete coating of carbon dioxide on the surface. Slightly greenish means there's some copper in there, some other mineral has come in, and you have not just calcium carbonate but different types of deposits. If you scrape away the top part, this is the calcite, out here you have exposed some basalts. We don't know at this moment if this changed as well, right? Has to change because you extracted calcite from somewhere. There are two different ways of doing this. One is what's being followed in Iceland. This is the CarbFix project, and this one here is the Walula project. Let's This is going to take longer. Let's do this. Let's stop over here and we'll talk about carb fix and volula tomorrow a little bit. We'll encroach on the EOR part, but we'll make up as we go through feed. Okay? So let's stop here because I think it's a lot of information and I don't want to sort of speak and speak and speak and not care about drooping eyes. Okay? Good. So let's stop here and I'll see you tomorrow. Thank you. Yes, and if you have questions, please ask. If you don't ask questions, then I'm impressed with all the chemical engineers having understood everything in geophysics.
Only question in terms of the 40 million US dollars, whether it is sufficient to complete the project, we feel it is very less.
What is very less? The 40 million? Yes, it is very little. Oh gosh, yes. We are looking for donors. We are looking for donors. No, but let me tell you what the project costs are due to. Here. $40 million, right? 8 million from the company. So 40 million, but this is what's coming from the government. 20 million go for drilling the well. Out completely. So we can't even count on that. About 2 million for core analysis. I can't do all the core analysis in my lab because we are not a factory. So we have to define, my lab will define protocols and say this is how we want the measurements done. That will then go to the company, they will do the measurements. That's $2 million. So now we're at $22 million, right? We're getting 32 million. The company's share is mostly for salaries, their salaries. So it's really not tangible cost for the project. We have social, yep. Which other one? There was one more, right? This one? Yes, yes. The pipeline study, yes. This is include capture system, yes. So capture system, but very superficial. We will not do capture systems. We will look at what capture systems work in the field over there. We have two cement factories. We have one steel factory. Those are the major emitters. So we think that we will have enough supply from them, but the capture facility, they will have to put in. We are not paying for it. No. That's not in there. But the pipeline, the study of which one is most efficient, all of that will have to be done by us. Pipeline, what type of pipelines we lay in will have to be done by us. These $20 million, right? Seismic data, 3 seismic data is about $2.5 to $3 million. So that's $23 million. The core analysis, Aeromag is $500,000. So that's 23.5, right? 23.5. $2 million for core analysis, that's 25.5. We're only left with 5 million for 3 years for 20 people to be paying salaries, students, postdocs. We are short of money. So we were looking at this. We made the assessment in 2022 when we put in the project. At that time, costs were very different. We were also not required to do chrome 25, which doubles our cost for casing. So we are right now doing rebudgeting and discussing with the government, with Department of Energy, to say, look, it took 2 years to permit, to get the project in place. In the 2 years, inflation and cost increase and a number of projects that are doing CCS has increased by a lot, mostly because the government has funded so many projects. And so now we are all competing with each other. So we are short maybe 5-6 million at least, if not more. That's what it seems like. So we can either save the money, right? We can fire students. That will save maybe $20. That's it. Students are cheap, but or we can cut the costs on analysis, which we don't want to do. So there is not much left for us to do. The only thing which we can do is to say we leave the science wells as science wells. We drill them, We get the stratigraphic, we get all the information we want, we cement them up, and we walk away and we say it's done. Sorry? Sure. The university could purchase the equipment, but we need people to do the work, right? So the students at Mines per year, I have to bring up about $70,000 per student per year. So it's not cheap. If we use undergraduate students, it's slightly less, but we still have to pay. And if you take undergraduate students, they have very limited time because we make them work hard for their studies. So they spend time on the weekends. We can't afford for students with less time to be doing this very quickly. I have been an undergraduate, I've had jobs like this, I know what we did. So I wouldn't trust myself as an undergraduate to do the job. I don't want to have undergraduates without proper supervision. As soon as we put in proper supervision, time goes away. Also, as you can see, there's the timeline, this one here. This is 1 year, right? 1.5 years we have to submit. We are 3 months into the project already, we have not drilled our first well. We will drill our first well, we'll get the data coming out in May. It's not the time to drill, it will be 1 month to drill the well. With everything, we can't drill in spring because snow melts, everything is muddy. We can't drill. We either drill in winter when it's frozen over, or we drill in summer. But in summer, we get migratory birds. So we have a very small time window. Most probably, we want to drill in spring, but before snow starts to melt. And that's our chance. It gives us most probably somewhere about 5 to 6 months to do all of the core analysis work. And we're looking at about 200 cores. The analysis will be porosity, permeability, those are fast as a function of pressure, right? Porosity, permeability, acoustic velocities as a function of pressure with different fluids, that takes a while. The fracture strength, that takes a while. The permeability for different fluids and relative permeability, that takes a long time. So those are, and if we have 200 samples, we need to sub-select and say, okay, we'll do every 5th sample for these measurements. Every sample gets porosity perm because that goes very automatically. So we have to cut corners. That's the challenge. We don't want to cut corners. If we bring everything we've done the calculation, we bring everything to the university, we get equipment, we don't meet our timeline. And the project managers are very clear from the government saying, this is not a research project. So we can try, we will do research on this, but that is just because we are taking part of the analysis money to define how the measurement should be done, and that becomes our scientific contribution. And then we keep doing the work, but that's about it. What else? We will have space here for students and for postdocs, most probably. That's once the core comes in. Once we can find the money to do all the work. No, we do have the money to do most of the work. It's just finding the extra money. But that's it's doable. It's not. We're not in a dire position to say we are in jeopardy of the cost. Now, one of the things which is a problem is this part here, the company here. They this one here is a problem because that's the commercial partner. The commercial partner, if you have followed the news, the politics in USA have changed, and so investments in carbon capture and storage are drying up. climate change is considered a Chinese invention. So, this is. I'm sorry, I get very. This is something that drives everyone. Um, is challenging. So if climate change is a conspiracy from other people, then investments in companies are not happening. Our partners, Carbon America, is a startup, which means they need investment. They're not, they have capture facilities, so they do cryogenic capture. That's their main main revenue source. But to do storage, they need investors. And what they've found is their sure investors, which were tied up and always in place, are going away. They are walking away from the project. So that's the threat. It's not running out of money, it's running out of a partner who has this money to pay their own way. That's the challenge. And that's going to be for most CCS projects in the US now. Sorry? Yeah, but by then our project is gone. Well, you don't, yes, that's true, 4 years. 4 years, and then he hands it over to the new guy, the vice president. Yeah. How does it change? Right. We don't know. We don't know. We think that this part here, the 32 million from the government, this is tied in law. So it will take them too long to change. By then we will have already spent the money. So we are okay. It's the part with investments. So the investment in CCS is drying up, which means all these partnerships cannot happen. They are being jeopardized. Most of the oil companies are pulling away from CCS. MIT, I just read yesterday, I was reading what's happening in the latest, and MIT has come up with a position paper on saying CCS is not viable. And I'm looking at that and saying, okay, you know, you put your flag in the wind, right? And whichever way the wind blows. So I really have to read what they're writing before I badmouth them. But at the timing of that article is very unfortunate. It's coming now at a time when markets are jittery about CCS. So I need to read that. Tomorrow you shall know more. You shall know as much as I do about the position that MIT is taking. Now, the challenge is for think tanks. If my university comes up, we are known for storage. If we come up with a position statement saying storage in the US is not safe, with that we have jeopardized most storage projects. So there is it's pretty much, if IIT Madras comes out and says, we have done a lot of work on capture, we don't think it is a good technology, we should stop all capture, the government takes notice. Projects are funded through these sort of position statements. Companies base their outlook on this sort of analyses, right? So that's the part which becomes challenging on how do you manage a very volatile political environment in the midst of uncertainty in investment, while still trying to do science and technology. So it could be the same thing in India. It could be that Niti Aayog, I think, is the funding agency and the think tank for climate change, right? If Niti Aayog comes out and says, no, the government changes its mind, or government changes completely, new government comes in and says, we don't think this is good. Niti Aayog comes out and says, yeah, it's not really a good thing to do. Everyone who's working on climate change or carbon capture, carbon storage, all of those projects suddenly have a very uncertain future. So sometimes the necessity doesn't matter. It's political reality that matters. Financial reality sometimes plays a bigger role than what is needed to be done. It's always going to be that way. It's never changed. So, anyway, we'll talk some more tomorrow about this. Yeah, thank you.